In this video, let us see about theory of simple bending. First, let us understand what is simple bending. Only bending is present and no shear forces are present. This is called simple bending. So if there is a moment applied here like this, there is a beam which is subjected to moment on both the sides. Here no force is present. So the shear force diagram will be, if this is the baseline, the shear force diagram will be this straight line only, because no shear force will be present in this. And what will be the bending moment diagram? If this is the baseline, this is shear force diagram. This is the baseline. If you see here, if we take a section here, it is rotating in hogging moment direction, sagging moment direction. So this will be a positive one. Here it is positive, and there is no force is acting and no moment is acting between the two ends. So up to here it will be a straight line. And if we take a section here and we consider the left side moment, this will turn the beam into sagging moment. So this is how we draw the bending moment diagram. If we see here in the shear force diagram, there is no shear force present in the beam, only bending moment is present in the beam. So this is called as simple bending. When only bending is present and no shear forces are present, then it is called simple bending. The stresses induced in this beam are called bending stresses. This is due to only bending, so these are called bending stresses. And some terminology is present while analyzing the simple bending concept. So let us see that now. First is neutral layer. The neutral layer is, if the beam is bent in this way, the beam is bent in this way, the top layers are under compression. These top layers are under compression, and these bottom layers are under tension. The layers below this neutral layer will be under tension, and layers above this neutral layer will be under compression. So in between these, a layer will be present. This layer is called this one. This layer is called neutral layer, which has no extension or no compression, no contraction or no extension. The length is not increased, or length is not increased, and length is not decreased. So that layer is called neutral layer. It is not under compression, it is not under tension. It is called neutral layer. And there is another one, neutral axis. Line formed by intersection of neutral layer and plane of cross section of neutral is neutral axis. So if you consider this body, the neutral layer will be at the center, because this is symmetry one. It passes through centroid. So this blue color line is the neutral layer. That layer is intersecting with the cross section at this line. So this is called as neutral axis. It is represented by NA. So this line is called neutral axis. The intersection of neutral layer with cross section gives us neutral axis. If a section is symmetric, material is homogeneous and isotropic, then neutral axis passes through centroid of the cross section. So if the material is symmetric means if there is an axis present, the left side portion should be same as right side portion. That is called symmetric. Or we can take like this also. It is symmetric about x-axis, and this is symmetric about y-axis. So if the cross section is symmetric, material is homogeneous and isotropic, then this neutral axis will pass through the centroid of the cross section. So at this neutral axis, the strain sign changes, because if this is neutral axis, the layers below the neutral axis will be under tension, the layers above the neutral axis will be under compression. So if we draw the shear strain distribution for this cross section, the layers under neutral axis are under tension, the layers above the neutral axis are under compression. So at this neutral axis, the tension is changed to compression when we travel from down to up. So this point, this is the point where strain changes its sign. Now let us see some assumptions in simple bending. The first assumption is the beam material is homogeneous and isotropic. In the introduction class of strength of material, we have seen that all the bodies we take are homogeneous and isotropic, and this is the assumption in every concept. So the beam material is homogeneous and isotropic. That means Hooke's law is valid up to elastic limit. The beam is initially straight and all longitudinal filaments bend into circular area with common center of curvature. So if this is the beam, initially the layers of the beam, if we consider these layers, these are straight, but when the moment is applied, it is bent into the shape. Then these all layers are under circular area with common center of curvature like this. First it was straight lines, and these are bent into circular area. And the next assumption is plane of cross section before bending remain plane after bending. This is called Bernoulli's assumption. This is very important. It may be asked in one mark question. So plane of cross section, which means let us say there is a plane like this, and this plane after bending will become like this. So the plane before bending is after bending the plane will remain same, but the angle is tilted, but it remains as plane. It does not distort like this. It does not distort. It will remain as plane only. Young's modulus is same in tension and compression. The upper layers are under compression and lower layers are under tension, but the Young's modulus will be same for tension and compression. We assume that. And radius of curvature is large when compared to the dimensions of the beam. So what does it mean? The beam bent is not when we compare the dimensions of the beam, the radius with which it is bent is very high when compared to this dimension. This is what it is said. So if we say this is the radius of curvature is r, and the dimensions of the beam are d is the depth and b is the width. This is the width. In 3D the width will be present. So we can write like this: the radius of curvature is very large when compared to depth and width. D is depth and b is width. And the next assumption is each layer is free to expand or contract independent of layer above or below it. So if I say there is a layer present here and there is another layer present here, these two layers are free to expand. This is not stopping the upward layer. So downward layer is not restricting the upward layer contraction, which means they both expand or contract freely. Any layer is not stopping its expansion or contraction when the load is applied, when the bending takes place. Now let us see the bending equation. In theory of simple bending, the problems are solved using this bending equation only. Let us see how we derive it. Let us say L is the length of neutral axis. This is length of neutral layer. The considered length of neutral layer. So L is the length of neutral layer, which is equal to NN. Before bending, it is equal to NN. So after bending it becomes N dash N dash. After bending it becomes N dash N dash, which is equal to R into theta. So this is radius and this is theta. We know that uh, if we take a sector like this, and the length of this arc will be this radius into theta. So length of the arc will be radius into angle. This is what length of the arc is given by. So here the length of the arc is neutral layer, which is n dash, which is equal to radius of curvature into angle theta. But we know that length of the neutral layer will not change. By definition of neutral layer, the length of the neutral layer will not change. So this length before is equal to length after. Let us say this is L dash. L dash is the final length and L is the initial length, but these two are same only. So L dash is given by AB, which is equal to, sorry, there is another layer AB, which is L dash. This layer downside of neutral layer, there is a layer AB. First it was like this, and after bending, the length of this AB has increased. So the first length is AB. The first length is AB means which is equal to the length of neutral layer. The second, the after length will be this AB. So what will be the radius of curvature for this layer AB? It will be radius up to neutral axis plus we have taken this distance y. So r plus y will be the radius of curvature into angle will be theta. So the length of AB will be r plus y into theta. The change in length of AB will be given by L dash. It is the final length minus L. It was the initial length. Initial length of AB is equal to neutral axis length. So we take it as L. L dash minus L is the change in length, which is delta L. So what is L dash? R plus y into theta minus what is L? It is r theta. So it will be, if we simplify it, r theta plus y theta minus r theta. So r theta gets cancelled and the remaining is y theta. And what is the strain? Strain will be change in length divided by length. So the change in length is y theta divided by the original length is r into theta. So theta gets cancelled and the remaining is y by r. But we know that the bending stress is represented by sigma b. The bending stress is equal to E into epsilon. So we can write sigma b is equal to E into epsilon is y by r. So we can write that sigma b by y is equal to E by r. So keep this equation aside and we next consider we have got the stress. Next consider the cross section here. If we consider this cross section, and this is neutral axis, and let us say there is a small area and the distance from this neutral axis is y. So what is this? The layer AB, the layer which we have taken in this AB. If we consider it in 3D, there will be a cross section for this here. If you consider that, then it will be like this. So this is the elemental area. Let us say area of this one will be dA. So the force on this elemental layer will be elemental force is equal to stress into elemental area. So we know that stress is equal to force by area. So force is equal to stress into area. So what will be the moment acting on this layer? If we take elemental moment, dm will be, what is moment? Force into perpendicular distance. The perpendicular distance is y. And now if we substitute df is sigma b into dA into y. So dm will be this one. So what will be the total moment? Total moment will be integration of dm. So integral sigma b y dA, and if we multiply and divide with y, it will be sigma b by y integral y square dA. But we know that this y square integral of y square dA will be equal to moment of inertia, sigma b by y into I, since integral y square dA is equal to moment of inertia, which is represented with I. So what did we get here? M is equal to sigma b by y into I. So sigma b by y is equal to m by I. We have got one equation. The sigma b by y is equal to E by R, and sigma b by y is equal to m by I. If we combine this both equations, we will get sigma b by y, which is equal to m by I, and which is equal to E by R. So this equation is called bending equation. It is called bending equation, or it can also be called flexural equation. So now we have derived the equation. Now let us see a small problem based on this bending equation. So there is CD layer which is lengthened by 0.03 mm. There is AB layer which is shortened by 0.09 mm, and the gauge length, the length we are going to consider is 20 mm. E will be Young's modulus is 2 into 10 power 5 Newton per mm square. So stress in the topmost fiber is, so what is the topmost fiber? It is the topmost fiber will be here. Stress in the topmost fiber, we have to find that. So how to calculate it? First let us draw the shear. It is lengthened by 0.03, it is shortened by 0.09. So it is given indirectly that the strain is given because gauge length is also given, so it will be change in length by original length. So if we draw cross section of this body, so the cross section of the body and there is neutral axis somewhere here, and there is 50 mm layer CD. The CD layer intersects the cross section here, and there is AB layer which intersects the cross section here. So this is 50 mm, and it is given that this is 100 mm. It is given here that it is 75 mm. So if we draw the strain distribution diagram, so how will it be? The upper layer are under tension because the CD layer is expanded by 0.03 mm, and AB layer is shortened by 0.09 mm. So the upper layers are under tension. So how will be the strain distribution diagram? The upper layers are under tension, so it will be on the right side, and the lower layers are under compression, so it will be on left side. If we join this, and what will be the strain at this layer CD, what will be the strain? So this will be the strain. This will be epsilon CD, which is equal to, so how much strain is induced in CD? Change in length is 0.03 divided by 20 is the gauge length. So 0.03 by 20 is the epsilon CD. Then what will be here? Epsilon AB will be 0.09 divided by 20. And this is, we know that this is 50. And we don't know this length. We don't know exactly that this neutral axis lies on the center or not. Let us say, take that y1 and this is y2. This is 75 mm. But we know that y1 plus y2 is equal to 100 mm. So y1 plus y2 is equal to 100. And what do we know? Yeah, there are similar triangles here, this one and this one. From this we can get y1 divided by this epsilon 1 is equal to y2 divided by epsilon ab. So y1 divided by epsilon cd, y2 divided by epsilon ab. So y1 from similar triangles, y1 by epsilon cd is equal to y2 divided by epsilon ab. So 20 gets cancelled, and the remaining is y1 by y2 is equal to 0.03 divided by 0.09. This will be 1 by 3. And 3y1 is equal to y2. And if we substitute this y2 in we know that y1 plus y2 is equal to 100. y1 plus y2 is 3y1 is equal to 100. So 4y1 is equal to 100. y1 is equal to 25 mm. So we have got y1 is equal to 25 mm. And now we can solve this. We know that sigma is equal to E into epsilon. We know this. What is E given? 2 into 10 power 5 into epsilon is 0.03 divided by 20 if we consider the layer CD. And this will be 300 Newton per mm square. So we got the sigma at CD. We know that there is an equation like this. Sigma by y is equal to constant, because sigma by y is equal to E by R is equal to M by I. So the ratio will be constant for any layer. If we say sigma CD by y1 is the distance of CD from neutral axis. So sigma CD divided by y1 is equal to sigma top divided by y top. So can we write like this? Yeah. And what is sigma CD? Sigma CD we got it as 300, and y1 we got it as 25 mm, and sigma top we need to find that, and y top will be, so y top is this layer. This layer from neutral axis will be the y top. So it will be y1 plus 50. y1 was 25 mm plus 50. y1 is 50 mm was the from top, and y1 is 25. So sigma top will be 300 by 25 into 75. 25 3s are 75. So this will be 900 Newton per mm square. So this is how we need to solve the problem. We have applied the bending equation and we have solved the problem. In the next video, we will see about section modulus and other concepts of simple bending. If this video is helpful for you, please like, share and subscribe.